I'm going to give you a harsh reality you may not want to hear. Grinding Arduino projects on Instructables or on YouTube or Adafruit or any of these websites that are doing those kinds of things will not make you a good embedded systems engineer. Arduino is a great hobbyist platform and it's a good way to start, but it is not a real representation of what embedded systems engineers do in their daily lives in industry. I've gotten so many comments about how do I get started in this industry, where should I learn, what should I learn? And I don't think there's a lot of good content on YouTube that really covers in depth what it's like to be an embedded systems engineer and what kind of knowledge is required. So I thought I'd make this full roadmap guide if you're interested in getting into the industry. I've broken down the key components of being an embedded systems engineer into 6 main categories, and here they are. The first one is general skills and the kind of mindset you need to approach embedded. The most important thing when it comes to mindset, in my opinion, for embedded systems engineering is this idea of big picture thinking. You are building an embedded device. It is going to form part of a larger ecosystem. It may have to communicate with other embedded devices. It may have to connect over Wi-Fi or cellular and talk to a server. It may have to connect to a phone over Bluetooth Low Energy, or it may have to connect to headphones or some of these other things over Bluetooth Low Energy. It has to be part of a larger ecosystem, and you have to keep that in mind when you are writing your code. Otherwise, you may find it integrates poorly into the large system, or you've missed something that's an essential requirement. This goes all the way down to the board level. So oftentimes on your actual circuit board where your embedded microcontroller is sitting, there are multiple different sensors and chips that all need to share communication buses and talk to each other. And so if you hyperfixate on one particular component, you might starve the others of resources or polling or something like this. So it's important to consider your whole system at the very high level, where we're talking about multiple devices, servers, things like that, all the way down to the individual components and integrated circuits on your PCB. Debugging is another really important skill to have. I'm going to be honest with you guys, a lot of the problems you'll encounter when you're doing this kind of engineering are very cryptic. It's going on at a very low level. There are multiple chips involved, there's electronic signaling, there's all sorts of things that you don't really have to worry about when you have nice, fully functional, high-level interfaces like an operating system. So learning how your code travels and how the CPU executes different code paths and how data flows through your application, learning how to visualize that and follow that is really important. We do have debug tools, but they're not as advanced as some things you get in a nice big full operating system. If you're wondering whether or not you need a degree to do all of this stuff, I have a full video where I talk about my personal qualifications and whether or not I think they've helped in this video right here. Without further ado, let's get into the technical stuff. So in terms of the platform is the base that you are going to build your application on. So the embedded application is the business logic. It's the part of the program that actually does stuff. But around that, you need some scaffolding. So the platform is going to be the building blocks of your embedded application. Now, for embedded systems, C programming is still king, all right? I've got that right here with this little crown icon. There are some efforts to bring Rust to embedded platforms, but they're not really properly supported by the manufacturers of the microcontrollers that you're going to be using. So good C fundamentals are essential to embedded systems development. So embedded C is not the same thing as system C. This is actually very important, guys. A lot of you might have done system C before, which is maybe things like socket programming on Linux, multi-threading, things like this. This is not necessarily the case on embedded. So on embedded systems, your code is usually the only thing that runs. There's nothing else going on the system, so you have full control over what the CPU is doing at any given moment, including hardware interrupts. This is stuff that is abstracted from you in systems programming and operating systems. So you have to keep in mind, your programming is the only thing that is relevant here. Nobody else's program is running except maybe the manufacturer's bootloader. The fundamentals are the same, right? So your if-else, switch, goto, your while loops, your pointers, function structs, but data types, you're going to want to learn about uints, so unsigned integers, and bit masks. Bit masks are huge in embedded devices. The concept of bits and bit masks, if you're only familiar with working on things on the byte level, you're going to want to learn about bits. The next really important part of your development platform is the actual microcontroller you're going to be using. Now I have two boards up right here that look kind of similar to an Arduino, but they're really not. The key thing to note is when I say microcontroller, I'm not referring to the board as a whole. I'm simply referring to this little chip right here. So on the right here, I have a Nordic Semiconductor development board, and this has an nRF52 microcontroller on board. On the left, I have an ST microelectronics board, which has an STM32 on board. There are so many different microcontrollers, and the reason for this is because each embedded application is so niche and specific, it can often help to pick and choose the hardware components that are actually inside the chip for the application. So for example, if you need to use a lot of input and output, you can get one with many GPIO pins, or if you need a lot of timing, you can get ones with lots of timers. If you need analog and digital features, you can get ADCs and DACs built on board, and we'll talk about all of these peripherals in the next section. But for now, just be aware that there are different microcontrollers. So for example, if you're familiar with Arduino, there is the Atmel and Microchip manufacturer. They merged into one company. So the Atmega series is, for example, what the Arduino Uno is based on. They also have the SAM and the PIC series. The Nordic Semiconductor chips, the nRF52s and others, are very, very focused towards Bluetooth Low Energy. So this is a high priority for these devices. The ST Microelectronics STM32 series is insanely popular. There are many guides on how to do things on STM32s, how to use the peripherals. ST provides great tooling like STM32CubeMX, and it's just generally a very well supported platform. Texas Instruments also has their long-standing MSP series, and there are many more. So just consider what hardware peripherals your embedded device is going to need when you pick the microcontroller, and we'll get to that in a bit. One of the most important decisions you make when beginning a new embedded application is whether to code bare metal or use an RTOS. This is very important because it kind of decides the architecture and general structure and how you write your code. Now, what actually is bare metal versus RTOS? So bare metal is, like I told you before, where your code is the only thing that's running. Every line of C or assembly that you write is what is going to get executed. There's nothing else in the way. With an RTOS, you do get some high-level primitives. So an RTOS, it stands for Real-Time Operating System. It gives you a kernel, a scheduler, some give you a heap. It can give you high-level synchronization primitives like locks. It can give you events. It can give you concurrency. So one of the main benefits of using an RTOS, like why you would want to use one, is to introduce concurrency into your application. Note, I say concurrency and not parallelism, because you still, in most cases, you can have multi-core embedded, but in most cases, there's a single CPU core that is executing, and the scheduler decides which task is going to run. So note the terminology differences. We're saying concurrency instead of parallelism. We're saying task instead of thread, because it's not technically a thread. In Zephyr, they use it threading as a nomenclature. In FreeRTOS, they use a task. I find task is better because it highly more differentiates between systems programming and the embedded world. But anyway, you have tasks that are essentially like threads in the systems programming world, but you have to be aware they don't execute in parallel. Your CPU is going to do one thing, and then you do a context switch to another task, and it's going to run that one. So if you do that very, very quickly in a smart way, you get something that looks like parallelism but isn't, and that's concurrency. So that's what an RTOS gives you. It gives you all of these nice features. It can give you data structures like queues as well. I know some people that just go and use an RTOS for everything, and I think that is fundamentally the wrong idea. There is a certain point, depending on the task, where bare metal is easier or an RTOS is easier. Do you know what I mean? Like, it actually becomes more of a hassle to use an RTOS if the application is dead simple. And it becomes more of a hassle to use bare metal if the application is more complex. So you really have to make that trade-off, because like I say, when you introduce an RTOS, you introduce a whole lot of extra complexity and a whole lot of context that you need to hold while you're building your application. Bare metal is simple but very basic. You rely on hardware abstraction libraries, MMIO, PMIO, and peripherals. This stuff, by the way, that's different colors we'll get to later in the video, so stay tuned. You have a cyclic executable. You might have heard this terminology used before. This is a very fancy word for a while one loop. I'm serious. It's a while one loop that loops forever. If you're familiar with Arduino, void loop is what the equivalent would be. But in real embedded, we use like while one or while true, and essentially this determines how your functions get executed and how your program responds to external stimuli. Interrupts and polling drive your bare metal application. So interrupts and polling are a very fundamental concept in embedded. Interrupts are hardware interrupts, so your CPU gets a physical, hey, let's go and do this. Instead of what you were doing, I need you to do this instead. And interrupt requests come in from hardware like I/O, they can come from timers, they can come from communication buses like I2C and UART. You can get interrupts from a number of different places. It's essentially something that forces the CPU to stop what it's doing and run some other piece of code. And this is really, really useful. Polling is where, for example, in your while one loop, you then go and check the value. Instead of the CPU getting interrupted and saying, hey, there's something available for you to read, or you need to go and do this, the CPU will check to see if that's the case or not. So that's interrupts versus polling. Polling is where you are checking whether a condition has been met continuously. Interrupts are where the CPU gets interrupted and goes and does something else. These two drive your bare metal application. Of course, they are important in RTOS as well, but you have extra fancy features to help drive your application, like scheduling. RTOS is really, really nice. It gives you all of that nice systems programming-esque primitives like you would see if you're programming on Linux, but it's very complex, and introducing it into your system adds a whole lot of things that you need to think about. Like you need to think about how your different tasks are executing in concurrently and things like this. You get events, software timers, blocking and non-blocking, so tasks can sleep and wake up. And this is a very similar concept to systems programming. And your interrupts and polling assist the application instead of driving it. You have a kernel that is driving your application. If you've decided that your application would benefit from an RTOS, there are two ones that everybody talks about. Of course, there are more, but these are the two big ones. They are Zephyr and FreeRTOS. So FreeRTOS is a very simple RTOS. It gives you a kernel, a heap for dynamic memory, and a scheduler. You can configure the stack size, the heap size. It's get up and go. On STM32s in particular, it is very, very easy. It's very easy to get up and running. Zephyr is a much more complex ecosystem. It provides drivers, so for example, if I have an I2C peripheral like an accelerometer, Zephyr might provide a driver for that. FreeRTOS does not. I would have to source that driver myself or write it myself. It provides complex and advanced configuration. The keyword here you're looking for is device tree, so you can research the Zephyr device tree. It's actually got a very similar configuration to how the Linux kernel is configured because Zephyr is supported by the Linux Foundation. And you have to check very carefully to make sure that it is supported because it has all of this extra stuff. Like it has a networking stack and everything. It's pretty crazy. It's like a full proper operating system. So just make sure that all your hardware is going to work nicely or you're going to have a bad time. This is one of the things that I've noticed. I've used both of these. FreeRTOS is much more simple and much easier to get up and running, and it's more flexible. Zephyr, you have to do things the Zephyr way, right? And if your hardware is compatible, you'll have an excellent time. It'll be amazing, super smooth, it'll just work. But if your hardware isn't compatible, you're going to have the most nightmarish experience possible. So keep that in mind. If you want to use Zephyr, it's amazing. Just make sure it's all supported. FreeRTOS is a lot more simple and a lot more flexible and might just be enough for what you need. Another really important thing for you to know about is a hardware abstraction library, or a HAL. Essentially what this is supposed to do is to add a layer of abstraction between your application code and the hardware of the device. In this case, we're talking about registers. So registers, the brief introduction to registers is that it is a space in memory where you can configure hardware of the device. So for example, if I put a value in this memory address, that will set this setting on my hardware. And a hardware abstraction library is supposed to sort of bridge that gap and make your code more portable. So for example, if the register I need to set to do function X is different on two microcontrollers, my hardware abstraction library is supposed to take care of that for me. The quality of hardware abstraction libraries differs greatly among implementations. Now I actually had to redo this section because the cicadas absolutely butchered the audio. I'm sorry about the previous section, by the way. This is just what I get for living in Australia. Now, hardware peripherals are very important. They are the building blocks that are available to you as the application designer. So your job is to understand the hardware peripherals that you have at your disposal, look at your requirements, and use the hardware peripherals to achieve that goal. These peripherals can be internal, meaning they are residing on the same chip as your microcontroller, they're all in the same integrated package, or they can be external. So they can be separate chips that are on your PCB that are connected to your microcontroller over some kind of bus. And we will talk about the communication buses that are commonplace in the very next section. So as some examples of peripherals, I have GPIO is the first one. This is typically what most people learn about. Like if you're looking at blinking an LED, you use GPIO for that. So GPIO is input output for the designer. That means you can use it for whatever you like. So if you need to set a pin logic high, or you need to read the value of a pin digitally, of course, GPIO is digital for the most part, you can do this. Now, they have logic levels, so for example, maybe 2.2 volts is considered a logic low, and everything above is considered a logic high. It's kind of just, I'll put an example on screen, it's kind of just like what voltage is considered high, because you'll be reading in some kind of input voltage relative to your chip voltage, which is usually something like 3.3 volts. Now, you can use GPIO to trigger interrupts, or you can poll for GPIO. So for example, one very common use case for GPIO is buttons. If you have a button interface and you push down on the button and your program gets an interrupt. That's one example of this. Timing is huge in embedded systems. In fact, a lot of applications are driven based off timing. So if your job involves checking things or doing a routine task every X milliseconds or even X nanoseconds in some cases, then you'll use timers for that. So timers can count up, they can count down, they can do all manner of fancy things depending on the microcontroller that you get. They can trigger interrupts, events, you can poll for them, etc. Watchdogs are another example. These are more of a reliability and fault tolerance kind of thing. So watchdogs ensure that your application is functioning correctly. Let's say that you want to, if you don't know what kind of bugs you have, you don't know if your system can get into kind of a weird state, a watchdog, you have to keep feeding it, essentially like giving it a value every X whatever time interval you like, otherwise it will reset your application. So you can use a watchdog to kind of restart if you crash or get into some kind of weird state. And usually chips will have these embedded into them. Now, the real world is analog, guys. When we're dealing with computers and stuff, we live in the digital realm, but the real world is analog. So I'm thinking about things like temperature, light, magnetism, sound. These are all analog quantities, and we need a way to interface our digital world with the analog world. And this is where our digital to analog and analog to digital conversion peripherals come in. So what they do is they measure or output a voltage. Now, a voltage can be variable, of course. We have variable voltage. In digital signaling, we typically think of low and high, but really, as I mentioned before, these are represented by a real-world voltage that just kind of gets rounded. So, for example, like 2.2, right, is low, and then anything above that is high. But, of course, we can have signals that are in between. And this is what our analog to digital converter allows us to do, is take one of these signals and pin it to a number within a range, right? So it just maps within a range. And I mentioned analog to digital converters and kind of talked about them before in a previous video that I will link in the description. Now, what digital to analog conversions can do is to get your digital microcontroller to produce things. So for example, it can produce sound. You can use a digital to analog converter to produce sound from your microprocessor. Examples of things that you can use to measure would be like a thermistor to measure temperature, a light-dependent resistor to measure light, a strain gauge for strain, and a Hall effect sensor for magnetism. Inertial measurement units, or IMUs, are also a very, very important thing. For example, your smartphone has an IMU in it that it uses to measure what orientation it's in, or like whether it's accelerating or decelerating, and things like this. So you can have main kinds of ones you can have are accelerometers, which measure acceleration, or magnetometers, which measure your device relative to the Earth's magnetic field, and you can infer all kinds of movement information based on these quantities. And of course, we need ways for our external peripherals to talk to our microcontroller. And I will let you guys in on another little secret. In some designs, you can have multiple microcontrollers on the one board. So we're not just talking about microcontroller to peripheral communication, we're actually talking about microcontroller to microcontroller communication. And this is one of the ways where you can get true parallelism in embedded systems, is if you literally physically have two microcontrollers on your board that are doing different tasks. Now, we have three big wired protocols that you will probably have heard of if you've done anything related to embedded before. These are I2C, UART, and SPI, or SPI. I like to call it SPI. And in fact, I have a big deep dive, I think it's like a 28-minute video on how these things work. It's called I2C, SPI, and UART, In-Depth Embedded Protocols. You can check it out, link in the description. The big ticket item to take away from these things is that I2C and SPI are typically one-to-many. So you have one master at the top who talks to multiple slave peripherals, whereas UART is one-to-one in a typical situation where you have one microcontroller that might talk to another microcontroller. Next up, we have some Internet of Things wireless protocols. There's a buzzword for you, Internet of Things. We have Bluetooth Low Energy, MQTT, and Zigbee. These are three important ones to know. BLE is great for local proximity-based data transfers and for devices that need to remember connections. It also provides a security layer with pairing. So BLE is great for local data transfer and streaming, things like audio or data transfer. You'll see this used very, very commonly. Here's an example of a BLE service hierarchy. I'm not going to get into the details in this video because I have a 25-minute example titled Hitchhiker's Guide to Bluetooth Low Energy. You can go check it out. Link, of course, in the description. MQTT is great for event-driven architectures. You have multiple clients that produce events in the form of publishing, and you have clients that are interested in receiving those events and responding to those events in the form of subscribing. So for example, I could have a temperature sensor that publishes a value, say the current temperature is this amount, and the controller for my air conditioner is subscribed to that, it gets that value, and it says, oop, I should turn the air conditioner on now. That's an example. You can have so many different things. It should be noted that this MQTT broker over here is a server, and this is implemented over TCP/IP. So your embedded device will need to be a bit beefier, and it will need to have Wi-Fi, cellular, or Ethernet, something that implements TCP/IP. But it's great for event-driven architectures and very, very commonly used. I've also written down Zigbee. Zigbee is a very popular protocol for home automation. It forms a mesh network. You have a coordinator in the center, and you have lots of devices around it that form a mesh network. For example, Philips Hue light bulbs use this. It's very, very popular for home automation, and it's good to know. Another one I want to mention is CANBUS. CANBUS is a little bit more niche. It's a wired protocol that is used extensively in automotive, industrial, and aviation applications. It's differentially signaled. And what do I mean by this? Differentially signaled is actually an important concept to know because USB, which is of course very popular, also uses differential signaling. I'll show you what this means in a CAN-bus context. So with CAN-bus, we have two wires, CAN high and CAN low. CAN RX is the decode of the bit stream. So CAN high, for instance, if we want to send a 0, CAN high goes to 1, and CAN L, CAN low, goes to 0. So what we're doing when we want to signal a 0 is we pull CAN L low, and you'll notice that CAN high goes to the opposite of CAN low. So what happens when we want to send a 1? So if you look over here, what we do is we pull CAN high low, and CAN low goes high. Why do we do this? Well, if you have a look, we've got some noise in here. Now, what we do typically is we do thresholding, right? We can say like, if it's above a certain threshold or below a certain threshold, then it's a 0 or it's a 1. But if we do differential signaling, we can take the delta, and what this does is, you can see this is not a perfect thing. It's a bit of a ramp, right? But if we take the difference between these two, we get a delta, and we can threshold that delta. And what that does is kind of automatically cancels out noise for us, which is really, really cool. One of the most interesting and daunting aspects of embedded development is how microcontrollers use memory. I know that memory management in C is everybody's favorite thing in the world to do, but I'm going to let you guys in on a little secret. We generally don't use heap allocations too much. In general, the purpose of embedded development, or one of the things that you strive to accomplish, is minimal usage of resources. And generally speaking, doing dynamic allocations willy-nilly is not really something we want to do. And we have access to the full RAM and the full flash of the CPU at any given moment in time. And so there's really not much reason to do this, because the situations where dynamic memory would be valuable, which is you don't know the size of something at runtime, occur a lot less frequently in embedded applications. They still occur, and if you have an RTOS, you can use dynamic allocations, but if you're programming bare metal, you very rarely do anything like that. You just use the CPU's RAM and the stack. Now, one of the more interesting parts of memory management is MMIO, memory mapped I/O. You might have heard this term offhandedly before. I'm going to tell you what it actually means. You might have heard me mention registers before. What I mean when I say registers in this context is a register of the CPU, so that's a place in the CPU's memory that has been reserved for hardware peripheral configuration. So those peripherals we were talking about just before, they might have different options that you can configure. So for example, a timer, you can change which value the timer counts up to. This is set in a register for that hardware peripheral, and memory mapped I/O is simply reserving a spot in the CPU's main memory where that register that controls that hardware peripheral can be set and changed. So for example, I have a place in memory I can directly address in the CPU's memory the value that that timer will count up to, and if that's ever changed during the lifetime of my program, that hardware peripheral will update its configuration. This is in contrast to port mapped I/O, where the peripheral address space is completely separate. So it's not in main memory. The CPU has to have special instructions in order to access these registers of the peripherals. And the benefit of this is that it doesn't waste main memory. So MMIO will waste memory addresses because they have to be reserved to be mapped to peripheral registers. Port mapped I/O does not have this issue. An example of something that uses port mapped I/O is Atmega GPIO. Direct memory access, or DMA, is essential for embedded device performance. What we've mentioned before is communication protocols like I2C or UART, where we have separate UART hardware that is inside the chip, or I2C hardware that is inside the chip, and we've talked about MMIO. So these hardware peripherals that handle this communication will have memory addresses in the CPU's main memory that they will store their results in. So for example, if I receive information over UART, that gets put in my UART peripherals MMIO memory addresses. Now, moving that from the peripherals memory addresses to my personal controlled stack memory addresses takes CPU time, because what I have to do is when I get my interrupt that says, hey, the data is ready, the CPU actually has to waste instructions taking the memory and copying it somewhere else. Because if we don't do that, then the data could get overwritten by the peripheral. So this is handled by a DMA controller. What a DMA controller does is it's smart enough to be able to take the results from your peripheral and put them straight into a user-specified buffer in main memory. And this speeds things up crazy amounts because the CPU isn't wasting time doing all of these useless copies. And so here we can see a typical DMA bus. So we have main memory over here, we have the DMA controller, the peripheral that we're interested in getting data from, and the CPU. And we all have a shared bus between the CPU, the DMA controller, and the main memory. So what's going to happen is the peripheral is going to talk to the DMA controller. The DMA controller is then just going to put that on the memory without the CPU ever knowing. And then once that data is complete, so once our data is ready, we can tell the CPU that data is ready, and the CPU can do something with that. So if you think about it, this is really good for large data transfers because we can do the large data transfer all with the peripheral and the DMA controller, and then only when that large data transfer is done will we tell the CPU, hey, data is ready, you should go and process this. This is really important for performance, and many microcontrollers have DMA controllers built into them, so you don't have to worry about extra peripherals. The last thing I want to touch on when it comes to memory are the different types of memory you'll see in embedded devices. The first type of memory is SRAM. This is fast and volatile memory. So if you turn the power off, this gets wiped. It's just like DDR RAM in regular systems, although it's quite different to DDR. So just keep that in mind. It's volatile and it works in the same way. This is used for your stack, your globals, and heap if you're using an RTOS. Then we have flash and EEPROM. This is slower, but it's non-volatile memory. It's used for constants. So typically the compiler and your toolchain is smart enough to optimize constants to go in flash memory if you mark them as const. Your program data and configuration is what this is used for. So for example, if the user changes some settings and I need to store that in non-volatile memory, I'll typically just write it to flash and then read it back from flash. It's important to note that just like peripherals, memory can be internal and external. So for example, here is a flash chip that is connected to the microcontroller on a SPI bus. And if you're interested in kind of knowing what's underneath the hood with memory cells, this is an example of an SRAM cell, and you can see that it's made out of MOSFETs. Now, this is one of the things that I learnt about in university/college. So it's a little bit complex and you don't really have to know about it on this much detail if you just want to build embedded systems. So don't worry about it too much, but this is kind of the internals of how a memory cell works, specifically talking about SRAM. We are at the final and potentially, for everybody who's been a software engineer before, the most scary part of embedded development, which is the electronics. Okay, what electronics do you have to know? It's not just software, guys. Now here's the deal, okay? If you want to be an embedded software engineer only and you just want to write code for microcontrollers, you just need a basic understanding of how the electronic stuff works, all right? You don't need to know how to design PCBs. If you're working in the industry, oftentimes you have an dedicated electronics engineer who will do the PCB designs. It is possible for you to just write software and never have to touch Altium or KiCad or anything like that. Of course, it does greatly help you if you know how to do this kind of thing, but you can get away with just being an embedded software engineer. Now, that being said, you do have to understand the fundamentals of electronics, and that is what we're going to talk about right now. So, the very basic stuff. All right, you got to know Ohm's law, V equals IR. The reason you got to know Ohm's law and also resistor dividers is because, as I mentioned previously, the real world is analog, and to interface that we use analog to digital converters, and Ohm's law and resistor dividers are essential in wiring up your resistive sensors. Here's the resistor divider thing I was just talking about. We've got the open circuit behavior over here on the left and the load behavior over here on the right, and we have these two formulas. So this formula here for the no load condition is very important for us. Like I mentioned before, when we're interfacing with the real world, it's all analog, and we typically convert these quantities to a voltage, and this is exactly how we do it. So we have some kind of resistive sensor. I want you to fix R2, all right, and we'll make our resistive sensor R1. So what a resistive sensor is, like for example, you have a thermistor, it will vary its resistance according to the temperature, and you have similar things for light. Now, if you fix R2 and you vary R1, according to this formula, you will get a different V out if V1 over here is constant. So if we keep V1 at constant and we have our quantity changing resistor over here, we will get a different V out that we can then measure with an ADC. And that's kind of how this works. And the datasheet will have a mapping for this component from what the different ADC readings actually map to in the physical quantity. Now, you also have to know how capacitors and inductors work, especially if you are doing things at a very high frequency. Your decoupling capacitors become very relevant. Capacitors and inductors are also very big components in filtering. So, for example, button debouncing, or if you're making a low pass, high pass, etc. filter. Voltage, boost, and regulation is very important as well as voltage levels. So, your microcontroller cannot take infinite voltage. I cannot stress this enough. You have to know what voltage you're going to give your little chip, otherwise he will explode. So check the datasheet for your chip. That's another thing you have to know. Datasheets are big documents where you can learn everything you would ever want to know about your component. So these are kind of the basic things that you have to know. Like, don't feed your chip 50 volts. You've got to know about resistor dividers and Ohm's law for your sensors and things like that. Capacitors and inductors are great in filtering. Next, we're going to talk about transistors. So transistors are electronic switches. You can think of them as, you've got the toggle switch, for example, in an electronic circuit, like a light switch. You can think of transistors as an electronically controlled light switch. You have two types of transistors, all right? You've got a voltage activated switch, which is a MOSFET, and a current activated switch. If you're unfamiliar with really how to think about voltage and current, voltage, if you can think about it like sort of a water pipe, all right? Voltage is the pressure that is being pushed through the water pipe, and the current is the amount, like, so the, the surface area of your pipe and how much volume of water is going through. Power, which is measured in watts, is voltage times current. Now, that's your two switches. They're the building blocks of CPUs, ICs, RAM, and flash. You remember in the previous section, I showed you an SRAM cell, which is made out of MOSFETs. These three gentlemen over here are integrated circuits. What integrated circuits are in concept is very simple. They are complex electronic circuits that are all put into a single package. So if you took the lid off these things and you tried to build the circuit that's inside individually out of individual components, it would get messy, it would get big, it would get hard to deal with. So what they do is they miniaturize all of these little things and they manufacture them into a single package like this. So a microcontroller, for instance, is an example of an integrated circuit. These look very similar to things we've seen before, like SPI flash, ADCs, those hardware peripherals we were talking about. You would buy them in integrated circuit form. Signals and filtering are very important concepts to understand as an embedded engineer, because a lot of the time, while filters can be implemented in hardware, it is cheaper to implement them in software. So as an embedded engineer, oftentimes you will be tasked with implementing a software filter. So understanding how to read signals and then how to filter them and how to represent them is a very important thing to know. We typically, when some of the terminology you might hear thrown around is quantization, continuous, discrete. So for example, if we are measuring a varying voltage signal, kind of like this one over here, right, that is continuous, and we want to turn that into discrete steps that the computer can understand, because think about this, guys, right? Look, computers cannot read continuous signals. You have to quantize them. That is what we're talking about. Quantization is the process of converting a continuous signal to a discrete one. Our computer needs to convert a continuous signal into a discrete one so that it can operate on it in steps, right? So for example, if I have a continuous signal, I turn that into little points that my system can loop through and understand. So that is the difference between a continuous and a discrete signal. And your filtering will typically be implemented in software on this discrete example over here. So we have a couple different types of filters that you need to know. So filters, high pass, low pass, and band pass. High pass means you allow high frequencies, low pass means you allow low frequencies, and band pass means you've got a sliding window where you can choose the frequencies to accept. And filters are used to extract frequencies from signals. So you can see over here, we have this signal that is comprised of multiple frequencies, and we can extract a frequency out of that. Electronic schematics are the main method of communication between the hardware engineer and you as the embedded software engineer, so you have to know how to read these. This is the formal definition of how the signals are wired into each other on the actual hardware. So of course, you're consulted during the design of this, but the hardware engineer kind of has the final say. And this is the formal definition of what your system actually is electronically. It's really important to know this because your devices and peripherals will be connected on different pins, and it's important for you to know how to use those. This is one of my schematics. If you want to see how I did the design for this, I will link the video in the description. And knowing how to read datasheets efficiently and to know what you're looking for is a serious skill that you're going to have to need, because these things are huge. A datasheet is essentially everything you could ever want to know about an integrated circuit, a hardware device, device, anything like this, and it will tell us, for example, about the UART. It will tell us about the I2C. It'll tell us about the digital camera interface. And I do intend on doing a future video specifically on how to read datasheets because it's a very important skill. You might be wondering where to go from here because I have just brain dumped pretty much an overview of the entirety of the embedded systems field onto you, and I understand that it can be quite overwhelming. So where do we go from here? My recommendation is this, guys. Don't buy an Arduino. If you're looking to get seriously into embedded and you're not looking to just be a hobbyist, I would suggest getting one of these to start off with. This is an STM32 Nucleo board. In a lot of cases, they are cheaper than an Arduino, and by using it, you will be learning real industry tools that people use actually at their jobs, like the STM32 Cube ecosystem. However, be very, very careful. The STM32 Cube ecosystem generates a lot of code for you, and you miss out on a lot of valuable learning opportunities by doing this. So what I would recommend is if you grab one of these boards, use the datasheet and learn about registers. So you can look in the datasheet at the register configuration stuff and have a go at setting up all of your peripherals using registers instead. You can recreate the classic like LED blinking stuff just using registers. That's excellent, and there are guides out there about registers. But once you've learnt the fundamentals, the hardware abstraction library and the Cube ecosystem can save you time by generating things. So I would recommend you get started with this. Once you're comfortable, you can branch out into more advanced applications, like maybe throwing in some extra, if you get two of these boards, you could connect them up over UART and mess around with that and things like this, or you could get something with Bluetooth or Wi-Fi or whatnot.